Alright guys, welcome back again to another video on this channel. So in this video we are going to be talking about capillary force. First of all, let's get a little bit of understanding. Capillary force, it refers to the force that arises due to the interaction of a liquid surface tension with a solid boundary, typically within a material. It causes the liquid to rise or fall in the tube depending on the liquid's adhesive or cohesive property, right? So let's look at this tube. This is our narrow tube, right? So here, as you can see, sorry, let me change the ink. So here we could tell that we have a good adhesive property, right? Sorry, ADH. And here we could tell that we have a good cohesive. I'm going to explain that. The behavior of a liquid in a capillary tube is governed by two forces. We have adhesive force and cohesive force. So for adhesive force, we have the molecules, right, interacting with the surface. But in our cohesive force, we have the molecules interacting with themselves and not the surface, right? So adhesive force are stronger than cohesive force. So in adhesive forces, right, the liquid are always trying to climb up the wall of the tube, creating a concave shape, right? So this is the liquid, this blue, right? As you can see, it is trying to climb up the wall of this tube, right? So this is our concave shape, which is like this U, like we are digging. It's giving us a concave shape. For our cohesive force, the liquid depresses, forming a convex, right? So as you can see, it keeps depressing. It's not trying to interact with the surface or trying to climb the wall of the tube. Rather, it is trying like depress itself. It's giving a convex shape. So seeing this convex shape, right, we determine that it has a poor wettability, and seeing this concave shape, we assume that our fluid has a good wettability, right? So let's go to this image. So let's talk about the capillary rise and fall. So the height to which a liquid rise or fall in a capillary is derived from the balance between the upward capillary force due to surface tension and downward gravitational force. So this is our upward capillary force and this is our downward gravitational force, right? To know our height, we have to create an equilibrium between our upward capillary force and our downward gravitational force, right? So from here, we could tell that to achieve our equilibrium or balance, we could go ahead and say 2 pi r, which is the radius, and sigma here, which denotes our surface tension, times our cos theta, which is this angle, right? The contact angle between the liquid and the tube surface, right? Trying to climb the wall. So equilibrium being equal to our gravitational force, which is pi r square times our h times density and acceleration due to gravity. So our h here is this height, right? Is this height of the liquid in the column, right? So making this h the subject formula, excuse me. Now making this h the subject formula, we derive the equation h is equal to 2 pi r, because we'll be dividing by what we don't want already. Remember, our sigma is our surface tension, cos theta, over things around h that we never wanted. We have pi r squared times density and acceleration due to gravity. Pi cancels pi, 1r, we are left with 1r. Nothing else cancels, so we go ahead and say our h is equal to 2 surface tension times r cos theta over r times density times acceleration due to gravity, in which some of us could go ahead and still solve because we know our radius is equal to diameter over 2. So since our radius is inverted, we have 1 over r, which is equal to 2 over d, right? So by the time we apply this into this formula, we could as well say our h is equal to 2 times our surface tension times cos theta over diameter, this time around, not radius, diameter times density, times our acceleration due to gravity, which is equal to 4 times surface tension cos theta, cos theta over our diameter times density times acceleration due to gravity. So both formulas here are for our h. We have this guy and we have this guy. So you could apply anyone. A question where you are giving radius, you know you have to apply this formula that has the radius. Questions when you are giving diameter, you know you have to apply this where you are giving this formula where you have the diameter. So looking at this image, for liquid that have wet surfaces, right? When our theta is greater than, when our angle is greater than 90, we know it has poor wetting. When our angle is less than 90, we know it has good wetting. But when it is equal to 0, we know that we have excellent wetting. So basically, all it is saying is that liquids that wet the surface, right, their angle theta is always less than 90. And cases when you have your angle theta greater than 90, just know that in that case you have a very poor wetting. And when it is equal to 0, you have excellent wetting. So let's go ahead and solve for this question, right? Excuse me, let me use green this time around. Let's go ahead and solve for this question. A glass pipe of inner diameter 2 mm. So as you can see, we have diameter here. Therefore, what do we figure? We are going to use the second formula, which has 4 times surface tension times cos theta over our diameter times acceleration due to gravity times density. Is the mass vertically in a water bed? Determine the elevated height. So we are told to look for our h, excuse me. We are told to look for our h. The surface tension and density is equal to this. So we are given our surface tension and we are given our density to be those digits. So and we are also given our contact angle. So remember, we are using this formula, which is 4 times surface tension, excuse me, times cos theta over our diameter times density times acceleration due to gravity. Okay, so guys, before we start solving, we need to pay attention to something. That our diameter is given as 2 mm. We can't go ahead using 2 mm. Why? Because our density is in meter. Our surface tension is also in meter. So it is required of us to convert our 2 mm into meter, right? Which is equal to 2 times 10 raised to the power minus 3 meter. That's our diameter. So this is what we'll be using in our equation. Don't make that mistake. So you can, at the end of the day, convert back to millimeter since our distance was given in millimeter. So inputting this in our equation, we get to have 4 times our sigma, which is surface tension 73. Sorry, let me use times cos 70 degrees, right, over our diameter, which is 2 times 10 raised to the power minus 3. Sorry, let me erase that and write it where minus 3 times our density of water, which is 998, times our acceleration due to gravity, which is 9.81. So let's punch that into our calculator and see what we get. Therefore, we have 5.1 meter. Remember, we converted to meter since all of our SI unit had meter. So if you want to convert it back to millimeter, you know you multiply times 10 raised to the power 3 to convert it to millimeter. And yeah, so guys, thank you very much for watching the video. Make sure you subscribe to the YouTube channel. Bye and peace out.